So here are the notes for week 11. And again, it's on chemical reactions. We're going to cover acid-base, combustion, and writing chemical reactions. So you'll be given a periodic table and all the polyatomic ions. So just on Unit 4 test, all that information will be given to you. You have to remember which ones are the diatomics. Now there's two things here. Solid phosphorus is P4, solid sulfur is S8, something that we haven't talked about yet, but it does come up in this. I think I'm just going to avoid that, but since it's already in the notes, I'm going to go with it and just tell you. So if we use solid phosphorus, then it will, I'll make sure to let you know. Now this is sort of combining a lot of things that you've learned, which is writing ionic compounds, writing covalent compounds, and balancing it. So a lot of this you know, and it's just simply you're going to have to work through them and practice them. And so the first one here is we have solid phosphorus. Remember, phosphorus is P4. Again, I probably won't, I'm not going to give that to you, but let's just do it because, it's not something I've mentioned before. Chlorine gas, though, is a diatomic. So if you don't know what the diatomics are, make sure you look them up. And those react to form phosphorus trichloride gas. So read this again here. Solid phosphorus, P4, chlorine gas, diatomic, phosphorus trichloride gas. We have the states of matter, and we just follow what the reaction says. So in a sense, we are rewriting the sentence in the language chemistry. So here, we want to balance this. We want to balance, everything but hydrogen, oxygen first. So I see that 4 in front of phosphorus. I can put a 4 there. And then we have 12 chlorines on the right. And therefore, I'm going to put a 6 in front of there. So this is a balanced chemical reaction for this. So something we need to return to and is mole ratio and limiting reagent. Now, this didn't always go over great. This didn't go over great. I guess it went over okay. I think it went over okay at the beginning of the year, but we're just going to return to it. And what the question is going to ask is, hey, we have this much phosphorus and we have this much chlorine. And how much product can we form from that much of each reactant? And the product can only be formed from the one that's going to run out first. So the thing that runs out is the thing that determines the product. So watch what we do here. We have 4 moles of phosphorus. Say we're given that. And we have to determine how many moles of PCl3 are formed. We know that 4 PL3 is formed for 1 every P4. So that means that 16 PCl3s are formed from the phosphorus that we're given. But yet you're never going to have the same amount of, the reactants are never going to react perfectly. So now we have 3 moles of chlorine gas, Cl2. 3 moles Cl2. Let's go coefficient of product, same thing, over coefficient of Cl. And we get 12, so 2 moles of PCl3. So that is the answer. I don't have any sig figs here. Maybe I should have, but that doesn't really matter. I just want to reintroduce limiting reagent to you again. And the answer is because, well, someone brought in 100 pieces of bread, which would be something like the 4 moles of P4, and 10 pieces of cheese, which would be the limiting reagent, 3 moles of Cl, then the product is going to be the lower of the two. It follows that same pattern. Mole ratio is what you want over what you have. If mole ratio verbiage bothers you, then just look at the pattern. It's not. Now here we have solid calcium chloride is formed by the reaction of chlorine gas and sodium solid calcium. Now, make sure when you read these that you know that this is saying formed, meaning that is going to be on the right. And if it's a ionic compound, meaning something on the left and something on the right, we have to look at the charges. So calcium is a 2 plus, chlorine is a 1 minus, and therefore calcium chloride is a CaCl2, and that's a solid. It is formed by chlorine gas, which is a diatomic. So if you don't know the diatomics again, look at them. There's 7 of them. Brinkelhoff. Just seems like if I had students in AP and they had a different sophomore chem teacher, they would always say Brinkelhoff. So these 7 right there are diatomics, meaning chlorine is always Cl2G, and solid calcium. I have the units, I have the matter, and this is already balanced. So, but I have the stages of matter in there, meaning solid, liquid, gas, or aqueous, and that's already balanced. Chlorine is balanced, calcium is balanced. There's 2 chlorines on the left, 2 chlorines on the right, and that's balanced. So here we're going to see how much product we can make from 2 given amounts. So if we have 4 moles of chlorine gas, so all these are 1 to 1 to 1. But let's just follow the pattern. So if I have 4 of chlorine, how much product can we make? I have 1, the coefficient of what we want, which is on the right side, or the products, over the coefficient of the reactants, meaning we're going to form 4 CaCl2s from 4 moles of chlorine gas. And calcium, we're going to just take what we're given. So if 6 moles of calcium, and 1 CaCl2 over 1 Ca, and we can form 6 moles of calcium, or 6 moles of CaCl2. So again, you can only make as many products as the least amount of things or the things that run out, or the lowest of these two. If we had unlimited Cl2, but essentially we're just going with the lower of the 2 numbers. So that is how many moles of calcium chloride can be formed. Now we have solid sodium bromide. So this is 2 elements, and it doesn't have the prefixes on, so we have to look at the charges. Sodium is a +1, bromine is a -1, so NaBr. And it decomposes. That means it breaks down into sodium and bromine gas. So it's so bromine is a diatomic. Oh, solid sodium. Oh, it does say solid sodium. I said because you're not really going to make sodium, a metal, into a gas. So it does say solid sodium right there. And that's just going to take a lot of energy. So here we have to balance it. These don't seem too tough to balance. It's just more so, I think, a matter of writing them out or knowing what's diatomic and what's not. But and I don't see any polyatomics in there as well. Anyways, we got a 2 in front of bromine. We're going to go over here. We have a 2 there. We have a 2 there. And as you'll see, a lot of times teachers want students to write this. Make sure that it's balanced, because, for example, there, 2Br or something like that is equivalent to Br2. So we have 2, 2, 2, 2. And so I'm taking this question off. So the question that you'll get will be like the last 2, just because I added some more stuff on. And so this is just somewhat of a curveball compared to the last 2, but I'm taking that off. So we're going to look a lot at combustion, and I think you'll see and hear a lot about combustion reactions in your career as a student and later on. So combustion reactions produce a lot of energy, and it's how we get most of our energy. But first, let's look at photosynthesis, because a lot of times students struggle with, well, am I supposed to know, what are the products and reactants and all that for combustion? And usually this helps out, where combustion is somewhat of the opposite of photosynthesis. So we know that plants take in carbon dioxide. Plants also need to water them, and then the sun. And they produce C6H12O6 and oxygen gas. For to balance this, let's balance non-hydrogen oxygens first, then hydrogens and oxygens. And so this is photosynthesis. And combustion is really the opposite of it, because combustion forms what plants take in, and what they need is a carbon-based compound and an oxygen-based compound. And they form energy. So the energy from the sun is what makes this glucose and makes this reaction happen. And the opposite is what combustion does. I'm going to balance a couple combustion reactions. That's all I really am asking, other than maybe to explain where energy is formed. And we're going to write just the, so this one's a little tricky. That one is weird. You're not really going to see that even if you take organic chem. But it's just the way that the homework does that. That 6 distributes in. And so C6, H6. Very, yeah, it's unique, I guess, but nothing too tough. But now we have, it's a combustion reaction. It says if no reaction occurs, it's always going to occur. So we know that if a carbon-based compound reacts with oxygen, it's a combustion reaction. And it forms maybe 2 things that you've heard of even before you took chemistry: CO2, carbon dioxide, and water. It doesn't matter which order you put the 2. I probably change it all the time. And so, and then we just got to balance it. And carbon's balanced first. So you want to balance it like, so like engineers always, so they become train drivers. And so all of you are going to be a train driver when you get older. And trains make the choo-choo sound. So we're going to balance it in that order. We'll balance carbon, hydrogen, and then oxygen. So we have to always add up 2 oxygens on the product side. We got 12 plus 3, that's 15. Now we have to use a fraction. So like what we did earlier, where we're going to put 7.5 here, because that's going to make it 15, because that's always an O2. So essentially, One way you can look at it is whenever you have combustion, whatever number of oxygen you get, you can put there above 2. So if you're not good at maybe dividing numbers in your head like that, if it's 17, just put 17 divided by 2. And then in the end, we just have to double everything. And so the final answer is going to be, if let's say that's a 1, 2, 15, 12, 6. You can check it by going carbon, we got 12, carbon, we got 12, hydrogen, we got 12, hydrogen, we got 12, oxygen, we got 30, oxygen, we got 24 plus 6 equals 30. So, that, I know I go through that quickly, but keep in mind that it just always works out. And if you're able to do that fraction, you're in good shape. And if it's taking you too long, start over and put a 2. Like, don't stop just writing numbers and doing crap. Just put a 2 in front of the most complicated one. So again, it would have worked here. So this is the same thing. I'm just going to show you how to add up these carbons. That 2 distributes in. So this can be written as CH3, CH2, C2H2, CH2, CH3. So carbons 1, 2, 3, 4, 5. Oh, there's 2 carbons here, so it's tricky. C6, H3, 5, 7, 9, 12. And then you just got to balance it, which H2O and CO2. Now, one more step with the difficulty of these, and that is where there's now an OH in the carbon-based compound. But it's the same thing. We got C2H6O plus O2 forms CO2 and H2O, where we're probably going to have to use a fraction. If not, we might not. So carbons here, we're going to have a 2 there. Hydrogens, we're going to have 3 here. On the right, we have 4 oxygens plus 3 oxygens. We need 7 oxygens. We have 1 oxygen here. So 7 minus 1 is 6. So we need 6. So we can put a 3 there. So this is balanced. Hence, we're adding up the oxygens there on the right-hand side. So I think you know how to balance the carbons and the hydrogens pretty easily. And then we have to balance the oxygens. And since there's already an oxygen in this complex one here, we're subtracting 1. There's not going to be more than 1. There's usually 0, but sometimes there's 1. We're going to subtract 1, and then we can put that 3 there. Keep in mind, if we have to put a fraction where that 3 is, we just put a fraction. It's always going to be a 0.5. Always going to be a 0.5. So 3.5, 4.5, and just multiply it by 2. All right, just some basic acid base is what we have to cover. If you take Chem 2, you'll do a lot more of this, but an acid is a compound that begins with H. It's that's not the definition you're going to hear in Chem 2, but it's good enough, and really, I think it's a pretty good definition. And then if you have acid and water, something that is acidic has a pH of less than 7. If it's basic and ends in OH, and it has a pH of greater than 7. And so like water, H2O, should be written like HOH. This is an acid and a base and a perfect mixture. So pure water, DI water, has a pH of 7. Now, what happens when you mix the two? Remember, it always forms water and a salt, meaning whatever So you can write HOH at the end, liquid, and then whatever is left. So those two form that, then NaCl, AQ. And that is what happens when you mix an acid and a base. And so let's do some practice ones. Let's balance the equation between magnesium hydroxide, or MgOH2, and HNO3. Keep in mind, it always forms a water. And then whatever is left, Mg and NO3. Nitrate is a polyatomic. Mg is a 2 plus. So that forms Mg NO3 2. So look at the polyatomic I gave you and see where I got that from. And HOH, that's water. There's a 2 there, so I'm going to put a 2 there in front of the HOH. Now, HOH is also water, but either way with me is fine. I wish that we wrote HOH that way because it does actually sort of show what it really is. And now this is balanced. No, it's not balanced, sorry. Oh boy. So we have now a 2 outside that NO3, so we're going to put that there. Now it's balanced. So if we're to check to see it's balanced, let's keep the polyatomics together. Magnesium on the left is 1, magnesium on the right is 1, NO3 on the left is 2, NO3 on the right is 2, hydrogen on the left is 2, hydrogen on the left, on the right is 2, and OHs on the right is 2, OHs on the left is 2. Now we got NaOH and another one, acid and a base, NaOH, H2SO4. We know it is a base and an acid. So I'm just going to write HOH first, and then I'm going to take whatever is left and make that salt. And so Na is a +1, SO4 is a -2, Na2SO4 plus HOH. You got to balance this, a 2, and then a 2, because we have 2 OHs, and therefore we need 2 OHs. Remember, HOH is H2O. And Alex, if you do the homework, you have to write H2O. But here, either way is fine. And so now this is balanced. And NaOH, H2, PO4. So that should be a 3. I'll update that before I give you the notes. So NaOH plus H3PO4. We're going to write HOH, whatever's left, plus 1 minus 3. And so that's going to be Na3PO4. Sodiums, I want to balance those. 3 there. I got 3 hydroxides, so 3 there. And that is balanced because we got 3 hydrogens. And so just look at the subscripts or the hints. So the 3 on the sodium's a hint, that 3 on that hydrogen's a hint. And so I'll give you, one of these and one of these, anything on the left with anything on the right. And you just have to balance it. And you'll also be given one where you have to work backwards. Hence, you have the product of the acid-base reaction to determine what acid base it is. And there's a lot of ways to sort of look at this. we know that water is HOH. The positive is going to go with this negative hydroxide. And so the base is going to be CaOH. I would then look at the polyatomic ions to see what the charge is of ClO2. It's a -1 charge. And then however many minus charges there are is how many hydrogens there will be. And this will be then the reactants. Now we would need, since there's a 2 there, we need a 2 there to balance it out. So, oh, it says here, okay, you can edit both sides. Okay, I'm sorry. So this would, you would have to edit the right side too. And CaClO2 2 plus HOH. Because there's a 2 there, we would then put a 2 there. And you would have to keep it as H2O and Alex, but you're working backwards. And keep in mind, whatever these reactants are going to be the same from that sheet I give you with the acid and bases on it. And so maybe, yeah. All right. So now this one's a little bit easier. We got NaBr and HOH. We know that we're going to have inners and outers. So we have NaOH and HBr. And this is already balanced. So those you can, I'm pretty sure they're going to ask for aqueous for these. Last question on your test is going to be determine if something's acidic or basic. Now, I'm making this pretty easy because I know that there's more and more is getting added up. So essentially what you have to determine is which one has more moles using one equation. Big M equals moles divided by liters. And if there's more moles of acid, it's pH less than 7. If it's more of base, it's pH greater than 7. And you're going to get an acid and a base to determine which one has more moles, and that's it. And then say if it's basic. So let's say we have, if you could do one of these, you can do any of these. And I'm doing this just because I haven't really touched a molarity much, and I should have. So I'm just throwing it in here. We have an acid, which is HCl. Big M equals moles divided by liters. And so 2.5 equals, we don't know, liters. Take the milliliters and move the decimal 3 times to make liters. So you've been doing that all year. And so the acid 0.0403 times 2.5. So I end up with sig figs, I get 0.10 moles of acid in a solution. And then if I have in a base, remember big M equals moles divided by liters. I'm going to ask it just like this because, again, it's new and the test has come up. And also, I just have to touch on molarity, as it probably will come up even if you don't take chemistry. Now we got moles later on if you don't take Chem 2. Divided by liters, I move the decimal 3 times. 0.0505. That is 0.17 moles of base. So the solution contained 40.3 milliliters of 2.5 molar hydrochloric acid, 50.5 milliliters of 3.3 molar NaOH. It's going to be basic because we have more base than acid. And so the last question, or this question, I'll probably ask something stupid for the last question, but for the second last question, it's as simple as that, where we're just going to take big M, moles divided by liters of the acid. Big M is moles divided by liters of the base. And the higher of the two will make the solution either acidic or basic. Remember, if it's acidic, it's below 7. If it's basic, it's above 7. And then, I don't know, if I threw a curveball and made them equal, then it would be a neutral solution. So pH is 7. So, all right, so that's it for, and keep in mind, it's always going to be just one hydrogen. So I wrote monoprotic. If you take Chem 2, you'll learn what that sometimes, if you have H2, PO4, then it's going to have twice as many hydrogens there. But, I'm just introducing it to you right now. So, so it's always going to be just one hydrogen. All right, so that's it for week 11. And, all right.